Welcome everyone. Thank you very much for attending this exciting presentation by Mononito Goswami, who is gonna try to defend his PhD thesis today. We'll see how it goes. We have all the committee members in attendance in person or remotely, so we can proceed. The way it's gonna happen is we're gonna let Mononito present his work for about 45 to 50 minutes. Then we'll open the floor to the questions from the committee members first. After that is accomplished, we'll be open to the questions from the floor from anyone here. After that, we'll excuse everyone from the room and have a private deliberation among the committee members about the fate of this PhD candidate. So let's wish him luck. And without further ado, Mono, the floor is yours.
Thank you so much. Good evening, everyone. Thank you so much for attending my PhD thesis defense. Today, I'll be defending my thesis, hopefully, on achieving pragmatic time series intelligence. A quick thank you to my committee, my advisor, Professor Artur Dabrowski, Professor Jean O, Professor Barnabas Potshosh, Laurent Callot from Amazon, and Professor Frederick Sala from the University of Wisconsin-Madison. Let's get started. Imagine you are a neurologist and you want to detect seizures using brain EEG data. Now you have to sieve through hours of data sampled at 240 hertz from not one, but 21 different leads. Basically, you must look at a very long and multivariate brain EEG time series to detect seizures. But that's not all. To make an informed decision, you must also review complementary information such as biological covariates in the form of text data or blood work in the form of tables. Basically, you have to review highly multimodal information. And to do that, you, our doctor, has to spend over 15 years studying and countless hours away from direct patient care. And this brings me to my first challenge. Domain experts must review complex and multimodal information to make decisions. Or instead, they can try to automate this process by building a machine learning model. Say you want to build a classification model to detect whether a time series shows a seizure or whether it is normal. To build a model, you'll first have to prepare data, pre-process and label it. Next, you'll build a model, train and tune it, and finally, you'll evaluate it. And at this point, you'll probably have to go back, rinse and repeat. Now, machine learning models, once built, can save time and lives. But building these models for a specific problem is tedious and repetitive. But the repetition and the regularity is also where the opportunity lies, and I will frequently leverage it in a lot of what I have done. Now, a friendly doctor has spent a lot of time, resources, and effort in building a machine learning model. But in the real world, data is seldom ready for machine learning. You have to accurately label your data. But if the nature of the problem changes even slightly, you will have to start from scratch. And all of that is assuming that your data is centrally located, but you might want to learn a collaborative model from siloed data. And this brings me to my third and final challenge. Preparing data for machine learning is a slow, cumbersome, and error-prone process. Alas, you have to repeat this effort for every new data set and every new task. And this specific example highlights 3 key challenges which limit the widespread adoption of time series machine learning. Building machine learning models is tedious and repetitive. To accurately model real-world data, just as domain experts do, machine learning models must also be able to review large volumes of highly multimodal information to make decisions. And finally, building machine learning models is bottlenecked by the time-consuming, cumbersome, and error-prone process of preparing data. And in this thesis, my goal is to develop tools to address each of these challenges. Now, building machine learning models is hard. It also requires experience. But what if you could build good time series machine learning models faster? What if we had time series foundation models, which given time series from different domains, could solve multiple different tasks, such as forecasting, classification, and more, without much training or effort? In the first part of this talk, I will present my work on Moment, a widely used family of open source time series foundation models, and convince you that it can, and already has, accelerated the time series machine learning development. Next, I will imbue my time series foundation models with the ability to model long and multivariate and multimodal time series. Domain experts must review complex multimodal information to make decisions, and so should our models. After Moment, I will present my initial work on Moment, a long context time series foundation model, and Jolt, our multimodal time series and text model. And until now, we've only focused on building capable machine learning models quickly. We've not addressed data challenges yet. For our models to be able to handle the challenges posed by real-world data, it is important for us to develop methods to encode expert knowledge, for example, to label data for training and evaluation. And this is precisely what the final part of my thesis will focus on. The overarching aim of this thesis is to empower domain experts with powerful, capable time series models to rapidly build machine learning solutions with all the complexity of real-world data. And to do that, to advance time series intelligence, I believe that it is important for us to build capable foundation models dedicated to time series data. It is important for us to improve our understanding of these foundation models, and also to address practical challenges that arise when common assumptions are violated. In the first part of this talk, I will demonstrate how specialized foundation models for time series data can accelerate time series machine learning. I will first discuss my work on Moment, the first family of open source time series foundation models, and then I will expand Moment's utility by building its long context and multimodal extensions. Now, advances in time series foundation modeling are very recent, and as such, very little is known about what these models are learning. The next part of my talk will focus on understanding these models to gain actionable insights with two goals: to improve our understanding of these models and their capabilities, and to improve their performance. The final part of this talk will briefly address critical real-world barriers to the widespread adoption of time series intelligence. Almost all time series machine learning models are built with the assumption that all the training data is centrally located, fully and perfectly annotated. But this assumption sharply contradicts the operational realities that we encounter when deploying time series models in practice. Now, I'm sure you all know about time series, but I'd like to build some common ground before I dig deeper. When I say time series, I mean a sequence of numerical observations obtained sequentially in time. Now, a typical time series is characterized by temporal relationships such as slow increases or decreases called trends, or periodic changes referred to as seasonality. And different features in time series can also be related. And time series data is ubiquitous. It is found in many different domains, for example, weather, robotics, economics, and healthcare. And effectively modeling time series data can have profound impact. Now let's get started with the first part of the talk, where I will discuss my work on Moment. Now, I've been using the word foundation models a lot, right? So what should foundation models for time series data look like? I believe they should have the same capabilities as what large language models have for text data. Take ChatGPT, for example. It can solve multiple tasks with fewer labels. It's multimodal and cost efficient once built. Therefore, I believe a time series foundation model should also have three key properties. They should be building blocks for multiple time series analysis tasks. And in this thesis, we show that time series foundation models can be used for classification, forecasting, anomaly detection, imputation, and question answering. They should be effective in settings with limited data, labels, and compute. And finally, we should be able to tune these models with n distribution and task-specific data to improve their performance. Now, there are three major ingredients to develop any foundation model: the data for pre-training, the model architecture, and training objective, and a benchmark to evaluate the trained model. Now, for a LLM, examples of this would be the pile, decoder-only transformer with next token prediction, and the MMLU benchmark. However, for time series foundation models, all of these ingredients were missing. There was no large, cohesive public data set which we could use to pre-train a model. So we introduced the time series pile, a large and cohesive collection of over 13 million unique time series from 13 different domains, such as healthcare, economics, robotics, and weather. Time series has many unique characteristics, which makes large-scale pre-training tricky. So we found systematic solutions to reconcile these unique characteristics to unlock large-scale pre-training, which culminated into Moment. And finally, there were no benchmarks to evaluate foundation models for time series data. Existing benchmarks were small, task-specific, and did not evaluate the unique properties of foundation models, such as zero-shot performance or scaling behaviors. So we built a benchmark to evaluate foundation models in 5 different tasks and also evaluated special properties such as scaling. And in this talk, I'd like to go a bit deeper into my design choice for time series foundation models. Now, the design space for any foundation model is huge. And I'd like to specifically discuss 3 important questions. First, how should we feed time series into the model? Second, what architecture should we use? Should we use a transformer or stacked MLPs, which are very popular in time series? And third, what should the model predict? First, let's talk about the architecture. I use an encoder-only transformer model. Now, transformers are a very common choice for foundation modeling in other fields, but they've also shown promise in time series forecasting. And using a transformer also allowed us to leverage advances in transformer architectures for language modeling, and as well as their efficient implementations. And finally, a transformer model, transformer encoder, has bidirectional attention, which is important for imputation, where the context can be both on the left and right-hand side. Now, to feed time series data into this transformer, we divided into disjoint time series subsequences of equal length called patches, and each patch is 1 token for the transformer model. Now, patches are great for 2 reasons, many reasons, I guess. First, attending on patches instead of individual time series reduces the complexity of attention. And second, thinking about the pre-training task, masking patches instead of individual time steps is a harder problem and forces the model to learn meaningful representations. And finally, I use masked time series reconstruction as the objective, because I realized that all the tasks that we're dealing with are instances of the masked time series reconstruction problem. For example, if the masked patches happen to be in the middle, we're doing an imputation problem. If they're in the end, the model is doing forecasting. In the literature, anomaly detection is typically solved using reconstruction or forecasting. And finally, to reconstruct time series, the model has to learn useful representations, which can then be used as features for classification. Now, we evaluated Moment on 5 different tasks and on multiple data sets from different domains, and compared it to state-of-the-art statistical and deep learning models. And I won't go over the results in depth, but we found that even with minimal hyperparameter tuning, it does really well. With all the parameters frozen, Moment performed on par with statistical baselines, for example, ARIMA for forecasting. And by just fine-tuning 1% of the parameters via linear probing, it was competitive with state-of-the-art deep learning models, such as PatchTST for forecasting. So the key takeaway is that unlocking this performance requires foundation models like Moment, requires large-scale multi-data set pre-training. And once pre-trained, foundation models like Moment can accelerate the development of good time series machine learning models on multiple data sets from different domains and multiple tasks. Now, Moment has been widely used in practice, and I will talk about it towards the end of the talk. Now, Moment, like most state-of-the-art time series foundation models, can only model short and univariate time series. Next, I will talk about how we can change that and build long context time series foundation models. I believe that a long context time series foundation model should be able to model both long and multivariate time series. In this talk, I will only focus on the multivariate extension. The key assumption here is that we can, with relative ease, extend multivariate time series models so that they can model long time series. Now, in the ideal case, we would like to model multivariate time series with minimal changes to moments architecture and the training procedure. But this is tricky because moment is a transformer, and standard transformers were designed to model text, which is a univariate sequence of tokens of fixed length. Now, a nice solution is to take all the channels of a time series and concatenate them to form a 1D array and simply pre-train moment with a larger context length. Now, this approach has many problems, but the biggest one is that it does not scale. Remember that the standard transformer has quadratic complexity of attention. Now, the key idea is to use memory in transformers. Now, on the one hand, recurrent neural networks process a single token and compute representations for arbitrarily long sequences. They're slow and optimizing them is hard, but they can model long sequences as we desire. On the other hand, transformers take a sequence of tokens as input in parallel, which makes them really fast. This sequence is called the context, but they do not maintain any state information and can only model sequences of a fixed length. Now, our idea was inspired from infinite attention, which marries the best of these both worlds. The key idea is to introduce a recurrent attention there with compressive memory. The compressive memory can store information from multiple channels. The attention layer can then attend to a sequence of tokens in context and in the memory. In standard attention, we can only attend to tokens in context. How can we then leverage the global information in the other channels efficiently? Well, we can add a memory unit where we can store cross-channel information. The memory compresses information from multiple channels. Then infinite attention proceeds in 2 steps. In the first step, the key and value products from multiple channels are aggregated into the compressive memory. Next, the query retrieves cross-channel information from the memory, just like it retrieves information from the context in standard attention. And finally, information from the global multi-channel context is added to the local context using a learnable beta parameter. And if you set beta to 0, then we approach standard local attention. Now, moment with infinite attention, or infinite moment, has some nice properties. First, we made minimal changes to the existing modeling and training paradigm. Second, with the knife solution, we scaled quadratically with the number of channels, but with infinite attention, we only scale linearly. And global multi-channel attention is invariant to the order in which channels are presented, which is desirable. And finally, we only add one trainable parameter, beta, per attention layer. So even the memory footprint doesn't grow significantly. We evaluated both moment and infinite moment on multiple multivariate datasets and tasks. Here I am showing multivariate forecasting results in 3 datasets, evaluated using mean squared error. We see that infinite moment consistently improves over moment. The 2 key takeaways from our experiments were that fine-tuning the beta parameters substantially improved performance. Recall that beta controls how much cross-channel information is added and fused into the local context. We also found that multivariate modeling does not always improve performance, and it will be interesting to study in what conditions multivariate modeling is significantly better than treating channels independently, like the original moment did. Now, onto the final section of this part, where I will briefly discuss our work on JOLT, one of the first multimodal time series and text models. Now, we are interested in modeling time series and text joint. This is a very rich problem space. We can take time series and text as input and predict either time series or text as output. In this talk, I will focus on the problem of generating text when a time series and some textual content is given as input. Now, generating text conditioned on time series is a useful task. Throughout this section, we will consider the problem of interpreting ECG signals, which are used to detect heart health. Now, doctors spend a lot of time away from direct patient care to provide clinical interpretations of ECG data, and this process is time-consuming, cumbersome, and error-prone. Some machine learning solutions do exist, but they're either based on hand-designed rules and are not expressive, and they do not generalize. And other approaches do not model time series data directly and instead convert it to either images or graphs. The key question is, how can we scalably generate expressive text by directly modeling time series data? The key idea is to align pre-trained foundation models. We can use Moment to learn meaningful representations of time series and use soft prompts to generate coherent text using pre-trained large language models. Our method Jolt then aligns the rich embeddings that Moment learns to the soft prompts to an LLM using a querying transformer based on the instruct blip architecture. We chose this architecture because Q-Forma has been used in literature to align image and text modalities for image captioning and visual Q&A. It also has some nice properties. I really love the idea of bootstrapping existing pre-trained models and moving the burden of alignment to another transformer, Q-Forma, which can now align time series and text based on textual instructions. Now, it is important to stress that we are in uncharted territory. There are no established data sets, tasks, or generic baselines. To evaluate Jolt, we use the PTB-XL ECG arrhythmia classification dataset, which is paired ECG time series and textual interpretations. We created two new tasks from this dataset: ECG clinical summarization, akin to image captioning, and ECG question answering, similar to visual Q&A. And you'll notice one thing. These statements look nothing like natural language. And yes, you are right, because they're not. These are basically brief ECG statements in German, translated to English. Now, on this dataset, we found that given an ECG, Jolt generated better clinical interpretations than BLIP2, which is a large vision language model which takes an image of an ECG as input. The first key takeaway from my work on Jolt is that time series data should be modeled explicitly instead of treating it as an image or a graph. And most importantly, for multimodal time series foundation models, we are bottlenecked by the quantity of good quality paired time series and text data, and not by technology. With this, we come to the end of part one, where we build capable, long context and multimodal time series foundation models. In this part, we will focus on improving our understanding of these models that we've built, with the hope that we can trust them a little bit more. And throughout this part, I will demonstrate that understanding foundation models can also help us improve their performance. I will specifically answer 4 questions. What are these models learning? Can we manipulate their predictions without retraining them? Do these models reason? And finally, do these models understand basic time series concepts? Now on to answering the first question. What is Moment even learning? The first thing we did was look at the pairwise similarity of Moment's hidden activations. The large version of Moment has 24 different layers, and hence we have a 24 cross 24 grid. The lighter color indicates higher similarity, measured using centered kernel alignment. What you'll notice is that some of the blocks of layers have very similar activations. This is very interesting and also very similar to how large language and vision models learn. And since groups of layers are learning very similar things, what if we skipped some of these layers to prune the model? And this is precisely what we did, and it led to a 50% faster inference time and only a marginal drop in performance. What you're seeing here is the mean squared error of vanilla and pruned Moment on some multivariate forecasting datasets. Also, this is task agnostic pruning. We do expect more savings if we started doing it in a task specific way. This brings me to our first insight on time series foundation models. They learn redundant representations. And reducing this redundancy improves speed while maintaining accuracy. Now, we have looked at how similar representations of moments are, but does it understand concepts that we as machine learning practitioners use to describe time series, namely frequency and trend, for example? So we first generated sine waves with different frequency and trend parameters. The parameter C there controls the frequency and trend of the generated time series, and different colors that you'd see would mean different values of C. And then we looked at the embeddings that moment is learning for these time series, projected to a two-dimensional space using principal component analysis. And what you'll notice from these plots is that as we vary the trend and frequency of the time series gradually, as we change the values of C, the embeddings that moment learns also gradually shifts, which tells us that time series foundation models are indeed capturing the language of time series that we as machine learning practitioners use. Finally, we wanted to dig deeper and understand where in moment is the model learning these concepts. So instead of looking only at the output embeddings, we started looking at hidden activations or embeddings of each patch and layer of the model. Now let's consider the concept of frequency. We again generated low and high frequency time series. We say that moment has learned the concept well if it can linearly separate examples with and without that concept in the embedding space of patch P at layer L. And since moment can do that, since it can linearly separate very high and low frequency time series in the embedding space at patch P and layer L, we can conclude that it is learning the concept of frequency there. And then we looked at the separation of these time series in the embedding space for each patch in every layer of moment. And in this plot, the lighted colors indicate higher separability. And what we found was, again, very interesting. Moment learned the concept of frequency at a specific location of the model towards the final layers and patches in the top left corner. Now that we know that moment has learned the concept of frequency at a specific location, we thought, can we use this information to steer time series foundation models? Now, one simple way to steer a foundation model towards a specific concept is to identify where it is learned, like we just did, and manipulate the hidden activations. For example, if we wanted to add periodicity to a time series, we can shift the activation towards the linear direction of high frequency time series in the embedding space. Again, recall, moment given a time series reconstructs it. So if I give it a time series with low frequency, it will reconstruct that. But now we can change the hidden activations of the model such that its predictions have higher periodicity. Here, the original prediction that moment would have predicted without intervention is in orange, and the prediction after intervention or after steering is in blue. And we can do this for other concepts too. We can add a positive trend to a time series, or also a combination of trend and periodicity. So by knowing where these concepts are encoded in time series foundation models, we can manipulate their predictions during inference without any retraining. Now, our examples are simple, but they can be extended to many real-world use cases. Now, concept steering can be used to generate synthetic data and introduce knowledge into the model that is not fully captured during training. And these inductive biases can be useful in domains like healthcare, where knowledge of treatment effects can guide the pre-trained model predictions about whether a patient's vital signs should go up or down in response to a specific intervention. And here I'm showing one specific example of steering an ECG heartbeat, which is normal, to an abnormal heartbeat. And at this point, we have some idea about these models, what these models are learning. So it was only natural for us to wonder if foundation models reason, or do they just simply memorize training patterns from large and diverse data sets? In our recent work, we explored whether time series foundation models and other deep learning models exhibit compositional reasoning. This is the ability to predict complex concepts during inference by combining simple concepts learned during training. We propose one of the first ways to assess compositional reasoning in time series foundation models. In this particular example, we train a model using simple single frequency time series and have it forecast multi-frequency time series during inference. We can also train these models on simple time series with only trend or seasonality and have them predict complex time series with both trend and seasonality. And now you must be thinking, I mean, this is extremely simple, right? You can certainly use inverse fast Fourier transform to decompose multi-frequency time series into its single frequency components. But the question is, can widely used deep learning models or our foundation models implicitly do that? And it turns out that even in the simple test, 9 out of the 16 methods we tested, including the standard transformer, not moment, the standard transformer, LSTM and linear models did not show any signs of compositional reasoning. But interestingly, we found that architectures used for state-of-the-art time series foundation models, for example, patched transformers and stacked multi-layer perceptrons, show sparks of compositional reasoning. Here you can see that when trained to forecast increasing trends or periodic time series, patched T5 or the moments architecture, and NBeats, a stacked MLP, can forecast complex time series with both periodicity and negative trends. Note that the model was never trained on negative trend. Most importantly, we found that input patching unlocks compositional reasoning in transformer-based time series foundation models, and transformers without any form of patching cannot reason. Now on to the final question in this part. Can our foundation models understand basic time series concepts? Now, we've been focusing exclusively on time series foundation models, but there has been a surge of interest in using large language models for time series tasks. For example, one recent work demonstrated that large language models can do zero-shot forecasting quite well. But it is unclear why LLMs can do well on time series data. So we developed a scalable benchmark to evaluate large language models in basic time series understanding categories such as pattern recognition and causal analysis. We proposed a time series exam, a collection of over 700 questions, procedurally generated at scale using templates. We generated questions from templates by randomly sampling time series and refined them using item response theory, which is also used in standardized testing such as GRE, and hence we call it the time series exam. So we randomly generate questions, but how do we improve their quality? For that, we use item response theory. We fit a 2-parameter logistic model, which predicts the probability that an LLMJ will correctly respond to the ith randomly generated question based on LLMJ's ability and questionize difficulty and its ability to discriminate between good and bad LLMs. To build the time series exam, we start with randomly generated questions, all 700 of them, and then improve them through 1 to 3 rounds of iterative improvement. In each round, all the candidate LLMs take the current version of the exam. We then fit the parameters of this model based on their responses. And then we drop questions with low difficulty and discrimination ability, randomly generate questions again, and repeat this process. From the time series exam, we derived several interesting insights. We found that LLMs do understand basic time series concepts, simpler ones like pattern recognition much better than complex ones like causality analysis. And secondly, when using multimodal LLMs to model time series data, we found that tokenizing time series as images to be better than text. But if you had to remember one thing from this work, that would be that benchmarks can be generated at scale. And this is really exciting in the age of benchmark contamination. This brings us to the end of part 2, and I hope I have been able to convince you that understanding time series foundation models can help us improve them. And here's a quick recap. I showed that foundation models learn redundant representations, which can be pruned to improve efficiency. I also showed that these models learn human interpretable concepts such as trends and seasonality, which are encoded in specific locations within the model. I demonstrated that we can leverage this to steer model predictions and imbue missing domain knowledge. Next, I showed that these foundation models show sparks of compositional reasoning, and it is input patching that unlocks this form of reasoning in transformers. And finally, I demonstrated that when LLMs are used to model time series data, instead of time series foundation models, target and scalable model interrogation can reveal capability gaps, which we can then fix using state. We have now built capable time series foundation models, and I have demonstrated that improving our understanding can help us improve them. In the final part of this thesis, I will address critical real-world barriers to the widespread adoption of these models. And specifically, I'll quickly summarize the tools that I've developed to deal with siloed, unlabeled, and mislabeled datasets. Almost all time series machine learning models are built with the assumption that all of the training data is centrally located, fully and perfectly annotated. However, in the real world, datasets are seldom labeled, and in fact, often mislabeled, and they're siloed. For example, a neurologist may want to train a model from data located in different hospitals, but may not be able to pool data together due to privacy regulations. When large datasets are available, they typically lack proper annotations. Domain experts must then manually and pointillistically label data, a process that is inefficient at best and ineffective when problem definitions evolve continuously, as is true in the real world. And to address these challenges, I answer 4 questions in this part. First, I show that to label data at scale, we can capture expert knowledge into labeling functions to programmatically label time series data. Even when data is labeled, the labels are not always perfect. And in fact, studies have shown that widely used simple benchmarks like MNIST and ImageNet have pervasive labeling errors, let alone the complex ones that we're using in our cases. And in this context, I introduced Aqua, a benchmarking environment to allow machine learning practitioners to pick the right cleaning method for their data. And when data is siloed and cannot be shared, I demonstrated that we can instead share labeling functions to label data and machine learning model parameters to learn collaboratively. And finally, on the evaluation side, I show that we may not always need labels to pick good models. I proposed the first unsupervised model selection method for anomaly detection models, where the key idea is to aggregate multiple imperfect sources of model performance. Metrics of model performance, sorry. And with this, I conclude the third and final part of my thesis. Now, prior to this thesis, domain experts worked alongside machine learning specialists to develop separate models for individual tasks. It was resource intensive and required substantial data, compute, and machine learning expertise. And in this thesis, I introduced foundation models as versatile building blocks for multiple time series modeling tasks. In the near future, I expect large language model agents to leverage these tools to fundamentally shift how domain experts are from being developers to strategic overseers. And I expect this evolution to decisively reduce human effort and transform how humans collaborate with AI across time series applications. In this part of the talk, I'd like to briefly discuss our ongoing work on large language model agents for time series AI. Let's quickly revisit our goal. I want to empower domain experts with time series intelligence on their fingertips. And this thesis until now has certainly provided tools that domain experts can use for their machine learning problems. But our tools, like most machine learning algorithms, expect at least some familiarity with machine learning to be used effectively. However, domain experts seldom have the time to learn to use these tools. So I wanted to make it easier for them to use the tools presented in this thesis. And none of this is far-fetched. Large language models have shown promise in coding tasks and simple machine learning problems. But these agents are built for and evaluated on Kaggle competitions, which is just tip of the iceberg. Kaggle competitions are great, but they have well-structured inputs and outputs. They have minimal ambiguity, and they have very few time series tasks. However, seasoned machine learning engineers have the ability to deal with much more involved problems. And therefore, I believe that building useful time series machine learning engineering agents will require us to go beyond Kaggle competitions. And this is where our ongoing work on the time series gym is situated. Beyond agents on the time series foundation models front, I believe there are many open questions. Existing models are trained on increasingly large time series datasets, but is data scaling all we need? I think future research should investigate information density of pre-training datasets and explore better dataset mixtures, as is common in large language models. And after working on Jolt and seeing the scarcity of paired time series and text data, remember the German statements in English, I wondered if you should prioritize building multimodal time series foundation models, or instead develop agents that leverage native time series models as tools while interacting with the world through text. I'm also excited about recent developments on scaling test time compute, and I wonder how we can effectively scale test time compute for time series foundation models. The answer may involve first equipping these models with some form of in-context learning. And finally, most state-of-the-art time series foundation models use transformers as backbone, but significantly vary in other design choices. And I believe that future work should investigate other architectures more amenable to sequence modeling and scaling. To conclude my talk, I'd also like to highlight some of the impact that this thesis has had. The datasets that we released have been downloaded over 10,000 times on Hugging Face. And in the 1 year that Moment has been released, it has received over 1.8 million downloads on Hugging Face, 500 stars on GitHub, and over $2 million in investments. And others have used Moment for a variety of tasks. They've used it for solar flare forecasting, diagnosing machine fault, human activity recognition, building predictive analytics, and have also found it broadly useful for anomaly detection and classification. In healthcare, Moment has been used to model brain EEG signals, photoplethysmography, or EEG, and intracranial pressure in the brain. And even some of my excellent colleagues in the lab have used Moment to model EEG and ECG data with some success. When I compared Moment with one of the recent foundation models for PPG called PapaGay, I found something really interesting. I found that Moment performs really well against the custom-built domain-specific model. Here, larger area is better. And this PapaGay was pre-trained on more than 57,000 hours of data, and Moment was not fine-tuned at all. Also, Moment has barely seen any PPG data. Now, this is not my own work, but I do expect that some fine-tuning with domain-specific data might improve results even further. Beyond Moment, this thesis has also made a few other open source contributions. And finally, some parting thoughts. I've come to the conclusion that all models, benchmarks, and metrics are wrong, but some are useful. For example, for anomaly detection, there is no single best anomaly detection model. And studies have shown that benchmarks have flaws, and the metrics to evaluate the models are also flawed. This naturally raises a question, like how should we even evaluate our models? And in this context, I believe that good benchmarks should be designed before building models, not as an afterthought. And these benchmarks should include multiple datasets from different domains and multiple evaluation metrics and scalable ways to generate the benchmarks themselves. Next, I believe you should prioritize building simpler models. It is quicker, requires less computational overhead, and we can always use a more complex method later if needed. And some benefits are not immediate. For example, for moment, using the standard transformer architecture allowed me to quickly explore mechanistic interpretability approaches, which you saw in the second part. That would have been harder otherwise. And finally, we do not need to know how to drive a car, just that it works and that we can control it. And I believe the same for AI systems, most AI systems. Some quick bibliographic notes, you don't have to read it, but trust me, the reviewer number 2 on some occasions did accept the papers we wrote. And finally, it takes a village to build anything meaningful. And without the help of all the people on this slide and the next ones, this thesis would have been a pale shadow of what it is today. Thanks to all my wonderful mentors in the Auton Lab, the Robotics Institute, Amazon, and at Google. Also Rachel and Dr. John Dolan for hosting the wonderful RISC program that I am a product of. To my awesome colleagues, some of whom are here and on Zoom. And last but not the least, my mentees. And without your enthusiasm, energy, and hard work, none of this would be possible. And most of my mentees who joined as undergraduates did go on to top graduate programs and positions in the industry, which should tell you very little about me and everything about them. To the most supporting and inspiring committee, thank you so much for supporting me, believing in me, and pushing me. Also, thank you to my advisor for advising me. And over the next 2 slides, I have a lot of pictures of friends. I think most of you are covered. I think this slide probably took the highest investment of all the slides I've made. I could not find my pictures with some of you, so I just have you guys there. I'm thankful to my friends back in India. You guys never made it feel as if we were 9.5 or 10.5 hours away. My friends in who are Bengali, who never spoke to me in Hindi when I spoke to them in Bangla, which I really appreciate. To my friends in the Robotics Institute, thank you for coming. And thank you for being there. Life in a country 10,000 miles away is not simple. And to my friends, there's another slide as well. You'll all find yourselves there. If you don't, then I did not have pictures for you. Trust me, I did scan my entire gallery. And to the Auton Lab, I feel like this is the best lab to be in. And if I had to do my PhD all over again, which I hope I don't have to, I would choose the Auton Lab. And finally, my family for so many things and whose love made it possible. My paternal grandparents are over my father, and my maternal grandparents are over my mother. So there was some thought that was put into this slide. But yeah, thank you so much. And here's a visual summary of my vision. I want to build agents which can operate with the real-world complexities of time series data. I showed a bunch of things. I do believe that time series intelligence can be substantially advanced by building capable time series foundation models, understanding these models, and addressing practical challenges. Thank you so much, and